In this video, I'll work through some sample problems on implications. For this first problem, we need to build a truth table for P or P implies not Q. So what we need to do to break this down is we need to think about the basic truth table for P implies Q. That's what we're going to have to keep in mind as we work through breaking down this more complicated proposition. So the basic truth table for P implies Q is, with our basic setup, P implies Q is true unless P is true and Q is false. That's the only time that we get a false from an implication. So what we're going to be looking for is when the hypothesis of the implication is true and the conclusion is false, that's when we're going to get a false for our implication. Okay, so when we break this down, we're going to kind of put this together in the normal way. So we're going to start with our P and our Q. We know that the last column of our table is going to be our full expression, P or P implies not Q. And then we just break this down. So if we break down the P or P implies not Q, we need P, but we already have P. And we need P implies not Q. So we'll make a column earlier in our table for P implies not Q. Now we're going to need P, which we already have, and we're going to need not Q, so we make a column for not Q. And now we're going to be able to put our table together. So we get TTFF, TFTF. So not Q is going to be the opposite of the Q column, so that's FTFT. P implies not Q, so now we're going to be looking at this and we're saying, okay, so P is true, not Q is false, and remember true implies false, that's the only time that we get a false out of our implication. In the next row we have true implies true, which is true, we have false implies false, which is true, and we have false implies true, which is true. So that's how we fill in that column. And now for the final column we have P or P implies not Q. So in the first row we have true or false, which is true. In the second row we have true or true, which is true, false or true, which is true, and false or true, which is true. So we get trues all the way down. And that's what our truth table would look like. So now we have a set of numbers, 2, 4, 5, 8, 11, 13, and we have a predicate, which is if x is odd, then x is greater than 7, and we want to know whether that statement is true for all elements of this set D. And if not, we want to find a counterexample. So we want to think of this first part of our predicate, if x is odd, as being our P of x. And then x greater than 7, that's our conclusion, Q of x. And remember, our basic truth table for implications looks like this. PQ, P implies Q. We only get false if the hypothesis is true and the conclusion is false. It's true every other time. So that means that if the hypothesis is false, it doesn't matter what the conclusion is. It doesn't matter whether Q is true or false. If P is false, then the whole implication is true. So the elements where P of x is false are going to be elements that make this implication true. So the elements of this set that are not odd, which are 2, 4, and 8, those are numbers on our list of that make this predicate true. So if P of x is true, then we have to additionally check whether Q of x is true. So P of x being true, that's 5, 11, and 13. So now we have to check for each of these numbers, is Q of x true? So is 5 greater than 7? No. So 5 does not make it on our list of numbers that make this implication true. Is 11 greater than 7? Yes. So there, the hypothesis is true and the conclusion is true, so 11 makes the entire statement true. Is 13 greater than 7? Yes. So there, the hypothesis is true and the conclusion is true, so the whole implication is true. So what we see here is that not all of the elements of D make this statement true. 5 is a counterexample. So when we're answering this question, the question says, do all of the elements make this statement true? The answer is no, because 5 is a counterexample. A counterexample is a value that makes the hypothesis true and the conclusion false, which is exactly what happened here for 5. Again, we've got an if-then statement, and we want to know which numbers make this statement true. So again, we're going to look at our hypothesis and our conclusion. And we know that anything that makes the hypothesis false is automatically on our list. So hypothesis false would be x greater than or equal to 5. So that would be 5, 8, 11, and 13. So those automatically make it on our list. But for the hypothesis being true, that's x less than 5, we only have two possibilities, 2 and 4. And so now we have to check the conclusion. If the conclusion turns out to be false, then that number doesn't get on our list. So is 2 even? Yes. So 2 makes it on our list. Is 4 even? Yes. So 4 makes it on our list. So in fact, all of the elements of this set D make this if-then statement true. And that's what the question was asking. The question says, determine whether the statement is true for all elements of D. The answer that we would write is yes, all elements of D make this statement true. Finally, we have a puzzle involving truth tellers and liars. So here we have two inhabitants. A says, I am lying only if B is lying, and B says at least one of us is lying. So the tricky part here is with this first statement. So we say, I am lying only if B is lying. So we have these different ways to construct these if-then statements in English, but when we say only if, that means that the prior statement, the thing that comes before the only if, that's the hypothesis. And then the second part, in this case, B is lying, that's my conclusion. So we would better rewrite that as, if I, meaning A, am lying, then B is lying. And that's going to make it easier for us to deconstruct this and solve our puzzle. Okay, so remember the way that we do this. Our first two columns are P and Q, where P is true if A is a truth teller, and P is false if A is a liar, and similarly Q is true if B is a truth teller, and Q is false if B is a liar. And now we have the statements that those two people make. So the first statement is what A says. So A says, if A is lying, then B is lying. And then B says, there's at least one liar. Okay, so let's first look at what A says, thinking about our if-then truth table. So we know that in the first row of our table, the hypothesis, which is that A is lying, that hypothesis is false. And remember, when the hypothesis of an if-then statement is false, the entire if-then statement is true. So that one's true. And again, in the second row of our table, the hypothesis of that if-then statement is false, which makes the entire if-then statement true. For a third row of our table, the hypothesis of that statement is true, because A is a liar there. But then the conclusion, which is that B is a liar, B is a truth teller in the third row of our table, and that means that the hypothesis is true and the conclusion is false, which means my if-then statement in the third row of my table is false. Finally, in the fourth row of my table, the hypothesis is true, A is a liar, and the conclusion is also true, B is also a liar, and so that if-then statement is true implies true, which is true. Now what B says, that's a little bit easier to analyze, right? B says there's at least one liar, and so that's going to be true in each of the last three cases, and only false in the first case, because if both of them are truth tellers, then there is not at least one liar. And so now we're looking for a consistent row, and the only consistent row that we see here is this third row, where A is a liar and B is a truth teller. So A is a liar, B is a truth teller, is the solution to our puzzle. So just remember, when you're working with these problems involving implications, a lot of what you need to do really just comes down to knowing that basic truth table for P implies Q. Once you know that and you know how to apply it, you should be in good shape.